Okay, so today what we are going to do is to look at lower bounds for problems. Okay, so we've looked at algorithms for a number of problems. Sorting, searching, finding median, finding max, min, matrix multiplication, all that. Now, at some point, you need to know: is there a better algorithm? When do I stop searching for a better algorithm? Right? Can we somehow say that this is the best you can do? Which is the same as saying that no algorithm can do better than this asymptotically for this problem, right? So that's what this notion of lower bounds is. So, for example, if I want to, so let's say the best, the minimum number of comparisons you can do, you need to sort n numbers, or you want to merge two lists, one of size m and another of size n, then an algorithm gives you an upper bound for this complexity. Okay, so you can say that we started out with an n square algorithm for sorting, insertion sort, selection sort, and then we improved it to n log n. So we know, for example, thanks to merge sort, the number of comparisons required to sort n numbers is at most n log n, right? Or n ceiling log n. Okay. Can you do better is the question, right? Similarly, we've seen for merging two lists of size m and n, that sequential merge, you just keep comparing, one pointer running on one list, another pointer running on another list will give you at most m plus n minus 1 comparisons. So these are upper bounds for the complexity of the problem. I want to know, can I do better, or you want to approach it from this direction, that can we show some lower bound for any algorithm to solve this problem, right? So now that's a hard thing because you are making a statement about all algorithms. Okay. So today, so in general, there are very few lower bounds known, and we will look at some of them today. And in particular, we'll look at techniques to prove lower bounds. Okay. So the first lower bound we want to show is that I'll explain what this means. Any comparison based sorting algorithm to sort n elements requires, it must perform, omega n log n comparisons. Right, so this is saying that no algorithm can do asymptotically better than this, and hence merge sort is asymptotically optimal. So in particular, you cannot expect a linear time sorting algorithm, is what this says. Now, this is actually saying something about a class of sorting algorithms. Comparison based sorting algorithms means that you are given a list, and the only way you sort by making pairwise comparisons, and then you learn something and sort them. Okay. There are other algorithms which don't necessarily sort by making pairwise comparisons. We will get to them later. Or maybe let's get to them now. So, for example, suppose I tell you my elements are in the range 1 to m, okay, or integers in the range. Then how do we sort? Can you think of a way to sort this?
Create a list of size m.
Okay, so create a list of size m, because I'm telling you that the numbers which I'm trying to sort are in the range 1 to m, right? So I will create a list of size m.
Every element encountered, just increase the size, increase the number of elements in it.
Okay, I need to initialize.
Initialize it.
So initialize this with 0. right? And then for x, or if ai is equal to j, let's call this some array m, then mj is mj plus 1. That means, so you have a counter which tells you how many zeros, how many ones, how many ones, how many twos, how many m's are there, which I initialize to 0. And as and when I see, I see a number 57, then I go to this array and increment this to say that I got one more 57, right? And finally, you output this, run through this array, because it is already in sorted order. Whichever is non-zero, you just output them in that order, right? Then output non-zero entries of m in order. So how much time does this algorithm take? Not quite. Mn. Okay, big O of n, Mn. No, both are wrong.
Mn plus
Why Mn?
Mn, I mean small m. So every time you are picking up an element and going through the.
Why going through the? I mean, it's an array. So how much time does this algorithm take?
This increasing.
No, overall, I'm giving you a sorting algorithm. Here is an entire sorting algorithm. How much time does this take? M plus n. Right? So I initialize this to 0. That's an order m time. It's an array. Why? I mean, it's numbers 1 to m. Why not keep it in an array? So I initialize, that takes m time, and then I run through an entire list, and this is again n time, and then the output. So this is order m plus n. Okay, and so that's an algorithm which sort of beats this lower bound, because that's not a comparison based algorithm, because I mean you are exploiting some extra information, that these numbers are in some bounded range, and you are not learning things by comparing pairwise elements. Okay, but whatever algorithms we have seen, insertion sort, selection sort, quick sort, merge sort, all of them are, they just compare pairwise elements and sort them. Okay, and the claim is that when you know no such information, and this is standard sorting algorithms will do these things. Any such sorting algorithm will require omega n log n time comparisons in the worst case. In fact, we will show even on the average to sort n numbers. Okay, so this is a very strong statement, because it's a statement about any algorithm. Okay, so how do we prove this? Okay. So let's think of, so suppose, how do we sort 3 elements? Let's say I have 3 elements, A1, A2, A3, and I want to sort them. What would be your algorithm? Yeah.
Here we can find, given a set of arrays, we can find the maximum in log n time. Find
How fast can you find the max?
max n. Yeah, in n time I can find the max.
Yeah, and then do this.
And then I get the bound, and then
Yeah. So how much space would you need? Suppose I'm sorting 50 elements in the range 1 to 10 million or something, right? So yeah, so you need that much space. But yes, it's an order m plus n time algorithm, but yes, it doesn't fall into this comparison based algorithm, because you're doing these kind of things. You're not learning things by making comparison between elements. Yes, you will need to do that to find the max, but after that, Yeah, so it takes too much space, right? Okay, but don't ever say that you can find the max in log n time, right? Okay, so if I give you three elements, how do you sort three elements? Compare A1 and A2. So let me write this like this, okay? I'll model it some sort of a tree, okay? So let's assume all elements are distinct, okay? No pair is equal, all are distinct. So then you have two choices, either A1 is less than A2 or A2 is less than A1. Then what do you do next? Compare, what do you, A1 with A3 or A2 with A3, something you will do. So suppose I compare A1 with A3. So you have two choices again. So if A1 is greater than A3 but less than A2, then in this case, you've done your sorting, right? Because A3 is less than A1, which is less than A2. In this case, all we know is A1 is less than A2 and A3, but we still don't know anything about A2 and A3, so we will make a comparison here. And if A2 happens to be less than A3, then you know it's A1, A2, A3. If A2 happens to be bigger than A3, then it's A1, A3, A2. And in this case, you will make some comparison. I don't know, A1, A3 or A2, A3, it doesn't matter. Okay, so if A2 is less than A1 and if it's greater than A3, then you know and in this case you may need to make another comparison and you will get this sort, right? Now any comparison based sorting algorithm will look like this, right? The only difference may be, what comparison you start off with. Instead of A1, A2, you might make something. But typically, all you're allowed to do is to make comparisons. You'll make a comparison. Depending on the outcome, you will make another comparison. Depending on the outcome, you'll make another comparison until you figure out complete sorted order. So I did it for 3 elements. But for any n elements, if you have a comparison based sorting algorithm, it will look like an algorithm will look like such a tree. Okay, let's call this a decision tree first, and any algorithm will look like such a tree. So you can model merge sort, you can model insertion sort, heap, selection sort, whatever sorting algorithms we have seen. So how does merge sort will do? It will take the first pair of elements and compare, and then the next pair of elements and compare. So in fact, after this, it can even do things in parallel, but you can, whether it's less than or greater than, it will make some same comparison, for example, right? Merge sort will take the first pair, A1 and A2. Regardless of what the answer is, it will compare A3 and A4. And then it'll, because it's doing pairwise comparisons. And then after finishing that round, it's going to do some merging where it will make some comparison. But essentially, any sorting algorithm, what I want to write, so any sorting algorithm can be modeled as such a tree, right? Internal nodes are nodes or comparisons, and edge labels are outcome of the comparison. Let's say to sort n distinct items. I even tell you that. Right? What can you say about the leaves of this tree? Solution, right? Output, yes, yes. Yeah, but for a sorting algorithm, how many leaves will there be? N leaves, okay. Yeah, so how many leaves will there be? In fact, you will see that when you do this 1, 2, 3, 4, 5, 6 leaves here, and each one would correspond to a permutation because it's A1, A2, A3, A1, A3, A2, because it's essentially if your input is one of those permutations, then you follow through this and finally you will sort it, right? If the smallest, yeah, okay. So a leaf in a sorting algorithm would be a permutation, and so leaves are permutations of 1 to n. Right? So for example, in this sorting algorithm, what is its worst case? How many comparisons does it make? 3, right? Because there are some lucky situations where I might just do one comparisons and I'll stop. But in this case, for example, so here I made 2 comparisons, I was lucky. But in the worst case, if my permutation is something like this, A1, A2, A3 or A1, A3, A2 for this algorithm. For a different algorithm, there may be different permutation. But what is the worst case or maximum number of comparisons? Made by the algorithm. What does it correspond to in the tree? Yes, there is a name for it, right? Maximum root to leaf path in a tree, height of the tree, right? Okay, so the observation is that any comparison based sorting algorithm, all it does is just makes a comparison based on the outcome. Sometimes it may not even use the outcome immediately. It might decide, like I told you for merge sort, it might decide to make some more comparison. Eventually looking at whatever, because outcomes is what it has learned. Based on whatever it has learned, based on transitivity of this partial order, all that, it will make more comparisons until it settles down on the permutation of the input, right? Because this gives you what is the smallest, next smallest. So your input could be in any of the n factorial permutation. So for each permutation, it will land up in one of the leaves, right? So that's all you need to know. Now we are ready. So the number of leaves is equal to, or at least what? N factorial, right? Because if some permutation is missed in the leaves, that means if your input is coming in that permutation, then your algorithm will get stuck. It may not actually give you the right answer. So every leaf, every permutation should appear as a leaf something. So number of leaves is n factorial. Now this is a binary tree because we assumed there are no equal pairs. They're all distinct. So you have a binary tree on k leaves, then you can say something about the height of the tree. Yeah. So here is an observation exercise. Any binary tree with k leaves has height at least log base to the base log k, right? Because if it has height k, then it will have at most 2 power k leaves. because it's just producing something that you can prove by induction. So, since the height of the tree is the worst case time for the algorithm, the worst case time for the algorithm we conclude is at least log of n factorial. So you just need two observations. Number of leaves must be n factorial, and so the worst case time is log n factorial. And log n factorial is it's actually theta n log n. So any sorting algorithm there must be some input. That's what it says, right? There is some permutation for which it should take you that much time. The height must be at least omega n log n. That's what it claims. Okay. In fact, we don't know. I think it's an open problem to find a sorting algorithm which performs exactly this many comparisons. Okay, asymptotically, if you don't, and if you, we have reached very close with respect to the constants in the front and the linear term and so on. So merge sort, and there are a number of sorting algorithms that will perform 1 in log n. But precisely at most this many comparisons, is there a sorting algorithm? It's known for some large values of n. In fact, Knuth had some experiments done very early on, up to some 100 or something like that. We know, or even larger number. We know exactly the best way to sort that many numbers to minimize the worst case time. But in general, we're pretty close asymptotically, even with constant terms. But yeah. Okay, and in fact, we can also talk about the average height. Okay.
Since it's log and factorial, does it mean that there exists at least once permutation
Right.
which takes us from root to leaf?
Yes.
So it's not possible to have all answers before that level.
Correct. Exactly. That if so, there is at least one permutation for which, so given any algorithm, so that permutation may change for a different algorithm. Instead of A1, A2, you started with A1, A3, it may be a different permutation. But for given any algorithm, there is some permutation for which it will take at least log n factorial number of comparisons to give the correct answer, because otherwise it wouldn't have learnt enough to sort. Okay, so and it turns out this is true for, so this height is the worst case, the longest path from root to a leaf. Suppose I define the average height, which is, go from root to leaf, just average over all the leaves. Okay, take a root to leaf path, take their distances and average them. That also one can show. That so average root to leaf path. So even on the average, again here the average means we're talking about average over all possible permutations. So here also n log n is the best you can do. So quicksort is sort of good on the average as well. Okay, so this is one way of proving lower bound, basically comparison based algorithms. You model it as a tree, and all you need to know is how many leaves are there. Okay, essentially all you need to know is how many leaves are there, and everything will follow, because it's just basically log of the number of leaves. Okay, so let's try it for merging. To merge two lists, one of size m and another of size n. must make, let's see how many comparisons. Okay, let's write down. Let's see. So you are given a list of size m, list of size n. Each one is individually sorted. We want to merge them. We want to create a final sorted list on m plus n elements. Okay. So again, you can model it as a comparison tree like this, depending on the outcome. So if your list is of some B1, B2, then any smart merging algorithm will not compare A1 and A2. Why? So you have given two sorted lists. You already know they are sorted. I mean, algorithm might make it. You never know, but you know the answer to this. So why do you even want to make this comparison? Typical comparison would be AI and some BJ. Right? Typically, your algorithm will make AI and BJ depending on the answer, another AI and another BJ, and that's how it will go. Finally, it will have a complete sorted list of A's and B's. Okay, how many leaves are there? Because that's all we need to know for a decision tree or comparison tree. M plus n factorial. Okay, so I'm just writing whatever he's saying. So number of leaves. So there is one suggestion which is m plus n factorial. Of course not, right? Okay. Because the arrangement on the m elements, arrangement on the n elements are fixed. You can't move them out. So what is the clean way of counting this? So I have a sorted list of size m, sorted list of size n. How many ways? I mean, what are your choices, right? I want to get the sorted list of m plus n, but these m elements and these n elements should retain their relative ordering because they are sorted. Okay. So any ideas? How many possible outcomes? That's all we are counting. So let's look at the final sorted list of m plus n elements, right? Now, where do you have choices? Where all A goes in, where all B goes in, that's where choices are, right? Because A and B are two sorted lists. You need to know where A goes and where B goes, right? So, what are the choices? So let's write down, okay? So I have, let's say A1, A2, A3 and B1, B2. I'm trying to sort these, okay? So what are all the possible things? It could be A1, A2, A3, B1, B2 could be one choice. It could be A1, B1, A2, A3, B2. It could be A1, B1, B2, A2, B3. How many such choices?
I'm not sure, but 4 choose 2 or 3 choose 3.
So for general M and N?
M choose M, M plus 1 choose N or N plus 1 choose M.
Yeah, m plus n, just choose any m from n and just put the a1 in the sequence.
And everything else is fine. So out of the m plus 1 locations for the final thing, choose where A goes in. How many choices are there? M plus n, choose M. There are m choices for the A things, right?
M plus N choose M.
Yes, because totally there are m plus n for the final list, right? So think of it as my final thing has my final sorted list has m plus n boxes, okay, out of which I decide where my first list A goes in, right? A has m elements, so I choose m locations and go and put my A there in this unique order. There is no choice among them anyway. And then everything else is fixed. Then B goes into the remaining locations in this unique order.
I wasn't thinking on this direction. Given say A's are sorted up array, so you have A1, A2, A to say AM. Then you have M plus 1 places where B can.
But among them, yeah, there may be several B's can get into one place and so on. So the way to think about it is finally, I have a sorted list of m plus n elements. I decide which ones have A. There are m choices. So I might decide, oh, these are all the choices where I'm going to put my elements A there. Once I fix the choices, everything is fixed because I have exactly the order in which A should go. The remaining location should be occupied by B in the same unique order. There is no other choice. So the number of leaves is m plus n choose n. So the number of comparisons must be log of, because A and B are sorted, right? They are appearing in the same order. In the final sorted order, among them there is no choice. You can't change them. They get in the same order. Log of m plus n choose n. So I'm going to write or log n factorial, and here it's log of m plus n choose n. Okay, the algorithm we have seen takes this many comparisons. Okay, maybe the lower bound can be strengthened. We know, so this is what we have learnt, right? We have an algorithm which takes this many comparisons, and we have a lower bound based on decision trees. I'm not saying necessarily, see, if you want a lower bound, you can always say a lower bound of 1, right, 0, or you can say, oh, I have to look at every element, so m plus n, something you can say, okay. Look at every element is not true every time, because something like binary search you can do without even looking at every element. So, but for certain things like sorting, you can say you need to make at least n comparisons. So some lower bound you can give. So the real non-trivial thing is to give a very good lower bound, very big lower bound, right? The lower bound gets strength if it is large, the upper bound gets strength if it is small, okay? So ultimately we want to narrow down. So for certain values of m, so let's say, suppose m is 1, okay, and n is n, then upper bound says n, lower bound says n plus 1 choose n, that's like it's giving a log n plus 1 lower bound, okay. There is a gap. I don't know what is correct bound. Can you improve the algorithm or improve the lower bound? Okay, these are questions. We will address them in problem sheet, okay. So I'm just going to leave it at this point, that we can prove this upper bound, we can prove this lower bound. Maybe both can be improved. Maybe there are certain cases you can actually get a better algorithm. Maybe there are certain cases we can actually get a better lower bound. Okay, both are correct. But the whole point I want to explain you is that here is a way to apply your decision tree and get. All we need to know is how many possible different outcomes are there. That's all there is, right? And then you will have, everything will fall in place. And I'm not necessarily saying that the lower bound you get will be nice, but it's a lower bound, okay? Maybe improvable, but so let's talk about searching a sorted list or something. So you have a sorted list and you have a query element and you want to find whether the element is there or not, right? So any algorithm will compare your query element and some element in the list. Again, it's not going to compare a pair of elements in the list because I know it is sorted. So it knows everything about pair. So so you can model it as a decision tree. Take some x and some ai. Depending on the outcome, it's going to make some x and some aj, and so on and so forth. And finally, at some point, you'll say, okay, x is in location A3 or A2, or it might say x is not there, right? So, how many possible outcomes? N plus 1 outcomes, n possible locations plus an outcome which says element is not there, because it might have made some comparisons, it just figured out x is not there. So, n plus 1. So, all you need to know is number of leaves, number of outcomes, and then you can, yeah. I am modeling any algorithm, right? So, remember, we are not developing an algorithm. We are saying that take any algorithm, I will model it as a decision tree and prove a lower bound for the height of the tree. That's all, right? It may or may not do binary search, but now because of this n plus 1 outcome, and so I'm going to say so the number of leaves is again is n plus 1 because n locations x may be or x is not n. Okay, so the lower bound tells you log of n plus 1 for the height, because you have a binary tree. The moment you find x, you will stop. So let's ignore the fact that you get an equality comparison at some point. So you have a binary tree with n plus 1 leaves, so the height will be log of n plus 1, that's a lower bound. Okay. What about finding max? Right, you're given an arbitrary list and I want to find the max. Algorithm will pick a pair of elements, compare. Based on the outcome, it's going to make a bunch of comparisons. And finally, it's going to say, max is in location A3, A5, A1, A2 or something like that. So, how many outcomes are there? N possible locations where x could be. So, number of leaves is n, because n possible locations. So, you get log n.
Why is it that right is
We will see. So, in fact, we will prove a tighter lower bound for max. We need a different strategy, okay? Not just the decision tree is somehow it's generally weak. Okay, it doesn't necessarily give you good tight lower bound. Okay, because it is somehow, it's also sometimes called information theory lower bound. It is somehow about what is the information you are trying to gather, and in one comparison, how much information you will get. But often it's not tight. We'll see. Okay, so log n is a lower bound, which is fine, but we know that we don't expect to find max in log n, right? I laughed at hit when you set. So why is that? Why can't you find max as log n? What is the intuition? You actually need to see every element. So we will capture this idea in a different argument, and we will try and prove some stronger lower bounds. Okay. But before so that's the next kind of, so one technique to show lower bounds is this decision tree, which works for typically comparison based problems, algorithms, and all you need to know is the number of leaves, and that immediately gives you the number of possible outcomes. Okay, and as I said, it's not necessarily tight all the time. So we will actually use a different technique called an adversary technique to prove tighter bounds. But before I do that, let's do one more common thing. Let's do reductions. Right? If you have done a course on computability theory and Turing machines, you would have seen there are problems which are uncomputable. There are no algorithm at all, and once you got the first problem, you will be able to show a lot of other problems by doing some reductions. Okay, and towards the end of this course, we will apply that in the context of efficient algorithms. Okay, but basically what I'm going to say is that because sorting requires n log n time, I'm going to use it to show a lower bound for some other problem. Okay, some other problem is something which you have looked at in your first assignment, finding a Hamiltonian path in a tournament. Right. So what is a tournament? It's a directed graph where there is an edge between every pair of vertices. Exactly one directed edge between every pair of vertices. So that's a tournament on 4 vertices. Okay. Now, so the assignment problem, if you have looked at, first question says that every tournament has a Hamiltonian path. Okay, you can actually prove by induction. And the second question says find it in n log n time, where here time means, think of the tournament is given in the form of an adjacency matrix, right? So 1, 2 up to n, 1, 2 up to n. Because there is every edge between every pair of vertices, all you need to know is the direction. Okay, is the edge going from I to j or j to I? So let's say we will present as 1 if I to j and 0 if it's going from j to I, right? At the ijth entry, you can say 1 means the edge is going from I to j and 0 means it's going from j to I. So then the problem asks you to find a Hamiltonian path by querying this matrix some n log n time. Okay. Now I want to show that okay, how to find it in n log n time? That's an assignment problem, and due date is next week, so I'm not going to discuss about it. But what I want to tell you is that you can't do better. How do you prove it?
These are the paths.
Hmm?
These are the,
Oh, you want to prove directly by decision tree? Okay, no, I'm saying, yeah, you can probably do directly the decision tree too, but I'm saying because you can't sort in n log n time, better than n log n, can I use that to say that you can't find the Hamiltonian path in, what is the connection between sorting and finding a Hamiltonian path in a tournament?
Maybe if we order the
Okay.
ordering will be the Hamiltonian path.
Okay, so let's be very careful. So what do we? So let's say Wait. Because it's the order in which we are proving is very important. So suppose I saw that we can find a directed Hamiltonian path in a tournament on n vertices in some f of n time. Okay. Then what do I want to show? You can sort. The claim is we can sort n distinct items using Fn comparisons. Okay, so time here meaning that Fn probes to the matrix, right? This is what we want to show. Now you
Suppose the
Sorting
vertices
to
are the numbers, elements of the array are the vertices, and we draw an array from A to B, if A is greater than B. And then we get a tournament because either A is greater than B or B is greater than A. And then we find Hamiltonian path, so we get an order.
is that clear? That's it, right? So it's almost important to write down the order of the reduction because you're going to get confused about what you're trying to reduce and so on. So it's useful to write it like this. What is our assumption? So the proof, given n items A1, A2, AN, model it as a tournament. Ooh. Where AI is less than J if and only if you have an edge from I to J, less than, greater than, doesn't matter, some convention, right? So this is, somebody has given you n items to sort. I will model it as this tournament and give it to this algorithm which is supposed to find a Hamiltonian path in the tournament, and that algorithm will probe some matrix Ij. That is same as asking a comparison between Ai and Aj. Depending on the answer, it will probe more things, and finally it finds a Hamiltonian path, and that Hamiltonian path will be a sorted order. Right? This is going to be a very useful technique as well. Reductions, right? You can use one algorithm as a subroutine to solve some other problem to prove lower bounds. We use it to show upper bound to design new algorithm, but this is to prove lower bounds. Okay, so we have seen one lower bound technique, and that's using decision trees or comparison trees, where you need to know the number of leaves in the tree to give a lower bound for the number of comparisons required. So we use that to show a lower bound for sorting, merging. Another technique I showed is to relate problems through the notion of reductions. Use the lower bound for one to show a lower bound for the other. We use that to show that finding a Hamiltonian path in a tournament requires omega n log n probes to the matrix. Now we want to get to a more powerful way of showing lower bounds, and that is the notion of adversary arguments. Okay, so think about how would you argue that any algorithm to find the maximum of a list of n numbers requires omega n minus 1 comparisons. The decision tree showed a lower bound of log n, but now we want to give a lower bound, stronger lower bound, in particular of n minus 1. Think about how you would do that. Any ideas?
Have I mean, if we have lower bound less than n minus 1, we must ignore one element we may not compare.
No. N by 2 comparisons are enough, right? N by 2 comparisons are enough to touch everybody.
I'll start with what
Is there any way that we can argue from graph-theoretic perspective to do it?
Yes.
I mean, take two isolated vertex. Okay.
Why should there be? I mean, what is a vertex? What is the graph? What is the graph?
can it be argued that
Yes, it can be. What is your graph? This one. Okay. Okay. So. Yeah. It's transitive. Yeah. I mean, if you're talking about directed graph, right? This is a directed graph. If you are using this graph,
Of as n component.
let's say I've made k comparisons.
Okay.
Okay. So how many edges will there be in your graph? No, because every comparison is an edge for you. So if I do k comparisons, you'll have k edges. Okay. Now you have to somehow bring in max somewhere, right?
Suppose we have the graph. So if there is a we are constructing edges. If a is greater than b, there is an edge from a to b.
So
But we are not doing for all. Then it will obviously take. So in the graph, from the max, there should be. I mean, it should be reached to each element by a. I mean, from the max element, every element should be reached by a sequence of edges. Right, there should be a path to each of the edges, each of the vertices from the max. So, I mean, basically, it will be a take the tree where that max element is the root, and there are in a tree there are n minus 1 edges. Connected tree to make it reachable. So, I have to make n minus 1 comparisons. So, I have taken all the elements as vertices, and now to declare one to be max, I need to, I mean, somehow show that it is, I mean, where in the graph I will construct edges. If a is greater than b, there will be an edge from a to b. So from the whatever will be the max element, there should be a path of, I mean, directed edges to each element, right? Or else I can't claim that that is the max element. Right, so
Either directly or through transitivity, I should have a path.
But there will be reachable path. So that will be taken the structure of a tree because it needs to be connected from the root to each of the points. And in a tree, it has with n vertices there are n minus 1 edges, so I need to make at least n minus 1 comparisons.
Yeah. So let's look at. It will be acyclic because you're talking about.
It's a tree also.
No, it's a number, so there is transitivity, right? If A is less than B and B is less than C, I mean, when will you have a cycle? If A is less than B, B is less than C, but C is less than A, then you will have a cycle. But I won't give you that kind of an answer. So suppose you have made less than n minus 1 comparisons. How will your graph look like? So here is a graph. Let's even make it an undirected graph, okay? So you have n vertices corresponding to n elements. Whenever you make a comparison, I draw an edge. undirected H. Okay. Suppose you made less than n minus 1 comparisons, then how would the graph look like?
Disconnect.
It will be disconnected, because to have a connected graph you need to make at least n minus 1 edge. So now you have two components, right? So your graph, I mean, you might have made this comparison, whatever, right? Maybe even more components. It looks like this, right? So what does that mean? What does disconnected mean? That between elements here and elements here, the algorithm learned nothing, right? So as an adversary, if you say this is max, I will say no, this is max, right? Because I would be consistent with all the questions, answers I have given. Okay, so let's formalize this carefully, adversary argument, and the way I would like to go about it is that what is, let's write. So I mean, what did we see in the decision tree thing? We said there is some permutation which will take you a long time, that corresponding to that height. So for every algorithm which corresponds to a tree, there is some path which is long. Okay, so think of the adversary's job is to give that long path. Okay, so there is a two-player game. Algorithm and adversary are playing. The adversary's job. So I am, as an adversary, I look at your algorithm and say, oh, you have not actually made n minus 1 comparisons. I will prove you wrong. Okay, how would I prove you? Okay, for this input, for the comparisons and the answers I gave you, what is the max? Oh, you are saying this is max. No, this is max, right? So I will give you a different input consistent with all the answers I have given. I can't, because, okay. So an upper bound, so what does it mean by you can sort in n log n time? What does it mean? What does it mean by, so you want to tell some physicist, I can sort in n log n time. What does it mean?
To make n-log comparisons. N-log comparisons.
Yeah, so just say it a little formally. What does it mean by?
There will be different log edges.
No, we're not talking about graph and stuff. Formally, what does it mean by you can sort in n log n time? Given any input, okay. Any input on, you're talking about upper bound. Yeah, given any input on n elements, there exists algorithm that will
Sort the array.
at most n log n.
C of
Yeah, so C n log n time. Actually, this quantification suggests that for each input you are going to use a different algorithm, right? So I would actually put this out here, right? So for sorting, for example, what is that algorithm? Merge sort, right? So you can sort in n log n means that there exists an algorithm which for all inputs on n elements will sort that A will some whatever fn time. I want to prove an upper bound of fn. Okay, there is some algorithm, for example, merge sort. That's what it means, right? That if we give any input, it will actually sort in n log n time. This is what it means by sort can be done in fn time. Now, lower bound question is sort cannot be done in fn time. Can you say this in logical term exactly? Suppose I want to show that's what I want to show. I want to show that max finding whatever, yeah, for all algorithms. there exists input for which A will take greater than Fn time. That's what it is, right? Because for every algorithm, there is some worst case input for which the algorithm will take more time. So it's a two-player game. So you are the best algorithm, and I, as an adversary, am going to give you the worst case input. Of course, the input depends on the algorithm. There is no universal input. Depending on the algorithm, I will provide you a bad input for which. Another way to say is that for every algorithm, there exists an input for which if A takes less than f of n time, A will be wrong, right? Because A will give a wrong answer. So I have, as an adversary, my job is to produce a worst case input for which A will actually, if it takes less time, it's going to give you a wrong answer. Okay. So let's play this game on not max finding. We'll come to max finding. We almost sorted out the max finding. Let's talk about searching a sorted array. We already saw a tight lower bound using decision trees, but let's also see it using adversary, right? The adversary lower bounds tend to be really tight because they actually model a good algorithm. If you have a lower bound, you can also turn it into a good algorithm. Okay. So what is the problem here? I have a sorted array, right? Okay. Another way to think of it is I think of a number and you have to guess that number by asking me yes or no questions, right? This is the way we formulated this binary search. I think of a number between 1 and n. You have to ask me yes or no questions and find the number. Okay. So what is a bad input? What number should I think of? So your job is to get to the number fast because you are the best algorithm. And I, as an adversary, my job is to force you a lot of questions. So what number should I think of? Yeah, right. What number should I think of to force you a lot of questions? I don't know what algorithm you are playing, right? For every algorithm, you are the best algorithm. I can't assume you are playing binary search. You might be asking me any question. So what number should I think of to force you a lot of questions? What he's saying is, don't think of a number. I will dynamically choose my number. So then all I can have is a strategy. So that's why we usually say adversary strategy. Because if you don't think of a number and you ask me a question, I have to answer. How do I answer? Right? If I have a number, you ask, is the number greater than 47? If I actually thought of a number, I can immediately answer that. If I didn't think of a number, I need a strategy to answer that. So what is the strategy I would use to answer? If I am asking, for what? Always say no.
And think of a number that satisfies those.
So let's say I am thinking of a number between 1 and 1,000 and you ask the question, is it less than 998? Should I say no? Because then you're going to nail me down in 2 more questions. So what should I do? So yes, that is a strategy, right? That is a strategy. So I have to answer. So this adversary strategy is depending on of course it changes based on the algorithm. Because the input changes depends on the algorithm. I might ask your entire algorithm, look at it and then tell you this number and say, here, you're going to take a long time for this. Or I can dynamically think of a number. So I think of a strategy, which is that every time you are asking me yes or no question. So I will say, if I say yes, how many choices will be left? If I say no, how many choices will be left? Choose the thing which gives me a larger number. Right? So adversary strategy would be choose your number in the larger range. then what is the best strategy for you? For the algorithm? Half, middle, right? Because this is what I mean by the adversary will also tell you a good algorithm as well. Almost always when you have an adversary strategy, it also tells you a good algorithm. Because if you ask anywhere else other than binary search tree, your range is going to be even larger than n by 2. So now, how many questions with this strategy? What would be the number of questions you have to make? You can write a recurrence relation, but the recurrence relation now is greater than or equal to. By binary search, we said because we said, oh, you ask one comparison, your range comes down by half, regardless of what answer you get. Now it will be greater than or equal to, because the way I am answering, you will be left with solving the problem in a range which is at least half, right? Because it may be even much more than half, but at least this much. So this gives you a lower bound of whatever, log n or log n plus 1. Okay. So always you think of adversary strategy, which is a way of how do you answer. So for every comparison, you should have an answer. Because so algorithm asks comparison, adversary gives the worst case input. So finally, I will be, at the end of the whole thing, you will see I would have had a number, because I will be consistent with what. And the point is that if you stopped here less than log n many questions, then I have a larger range than 1. So if you say, maybe my range is 7 to 10, and if you say my number is 8, I'll say no, my number was 7, because consistent with all the answers, there are many choices left. So algorithm would not have learnt. That's way to show adversary argument. Okay. So there are quite a few problems where you can prove lower bounds using adversaries. So for max finding, the adversary doesn't have to work hard at all, because we analyzed it, right? I'll just say, I think of some list and I keep answering it, right? I don't remember, this is all I never give you what the number in the array is. That's the non-comparison based algorithm, where you look at AI and get the value. Here, the only thing you know is which is bigger, which is smaller, right? So at the end of it, if you did not have a connected component of edges, then I'll watch and say, if you didn't do n minus 1 comparison, if you pick up from this component as the largest element, I will pick up from that element, and I'll say, yeah, that's a larger number. And it is, so all you're saying is consistent with all the answers. There are several input arrays and several answers possible. So algorithm would not have learnt if it had made less than n minus 1 comparisons. So let's do a little bit non-trivial adversary, and that is to finding min and max. So for example, you can show that if you want to merge two elements of list equal size, then this lower bound is tight. You can come up with an adversary argument to prove this. Okay, so we'll handle it in an assignment. So let's do min and max. What's the best algorithm for it? Have you? I wonder. Okay, so let me prove a lower bound and tell me what the flaw in the argument is. Okay, so we have seen that max finding requires at least n minus 1 comparisons. Okay, because if it's not connected, I have choices. Same argument will hold for min finding as well, right? So min requires n minus 1 comparisons, max requires n minus 1 comparisons. So min and max require n minus 1 plus n minus 1, and that's 2n minus 2 comparison. Do you agree this? No? Why not? Yeah, a better way to answer that. So, you have an answer? When you say min requires at least n minus 1 comparisons, under the assumption that I know nothing about the list. I start fresh, the clean slate, you give me n numbers, I want to find the min. The connected component argument says that you need at least n minus 1 comparison. Similarly, max. But you can't, because when I find the min, I learnt a lot. Some various pairs of comparisons, some outcomes I've learnt, which I could take advantage of. So when I apply this argument twice, when I say max requires n minus 1 comparison, I am not in the ground zero state of knowing nothing about the input. I would have learnt something. Okay, so this lower bound doesn't hold. But what would be an algorithm? Can you think of a good algorithm to find min and max? Okay. Okay. Yeah, okay. Okay, so you find min and max here and min and max here. Then
We compare min of left with min of right.
and output, that's the min.
Yeah.
And similarly, max of the two should be the max.
No.
Why not?
Maybe the min of this side would be greater than the max of left side.
I mean, this max beats this anyway. So if I compare the two max, so what would be a recurrence? So it's fine. So my T of n would be 2 T of n by 2 plus 2 comparisons. You compare the min and max. Yeah. Yeah, so this is fine. And let's, you want to solve this? Okay. Oh, it does. I mean, we don't want asymptotics, because asymptotically we can do linear comparison. So I want more precise, but we can try and see if we can get more precise bound. It's linear because you can find min and max in linear time. So I really want more precise comparison, but this is a precise bound anyway. So let's see, 2 into, assume n is the power of 2 and all that. 2 plus t of 2t n by 4. So this is 2 plus 2 square plus and when there are two elements, you make one comparison, right? So if n is like 2 power k, t of 2 is 1. There are two elements, you make one comparison, you get this. So 2 cubed plus some 2 power k minus 2 plus 2 power k minus 1 into t of n by 2 power k minus 1, which is 2, which is 1. Okay, are you with me? Because it's finally you will have 2 power k minus 1 into t of n by 2 power k minus 1. N by 2 power k minus 1 is 2, t of 2 is 1, so that's this. And you have it actually up to 2 power k minus 1 here. So it's, I've never done this, but it's correct and it's fine. It's 2 into 1 plus 2 plus up to 2 power k minus 2 plus 2 power k minus 1. So this is 2 into 2 power k minus 1 minus 1. So this is like 3 into 2 power k minus 1 minus 1. This is, in terms of n,
N by 2.
Yeah, 3n by 2 minus 1.
1.5.
Which is 1.5.
Yeah, yeah. So it's actually minus 2, right? This is a minus 2. I was wondering. And it turns out this is correct. This you can do it for any n, not necessarily power of 2. There is another simple algorithm. I mean, this is fine. This is perfect. You just natural divide and conquer, apply, solve it. I just assumed n is a power of 2, otherwise it gets messy and you need to do careful calculation. So, suppose I apply this tournament method to find max. Okay, you know the tournament method to find max, right? Pair them up, pair everybody. Winners move to the next round, winners move to the next round, and you go all the way and you get the max. And that's how many comparisons? That's also n minus 1 comparisons. Now, how many more you need to find the min? Why?
Because we will know the minimum, the
Oh, at every level
numbers
when
is
we
lost in the
count.
first round, and
That's it. You need only the first round losers. Find a min among them. That's like n by 2, because anybody else who has 1 are not going to be min. So take the first round losers, there are n by 2 of them, find a min among them. So it's n minus 1 plus n by 2 minus 1. So that's 3n by 2 minus 2. Okay. Now, we will show that that's the best. You know, any algorithm, I will give you an adversary argument which will show that to find the min and max, it requires at least that many comparisons. Okay. So, somehow, see, both are playing the same game. Algorithm and adversary are trying to play the same game. So, you somehow want to model the learning of the algorithm in some way, and then you will see that the algorithm is trying to minimize, maximize that learning, and the algorithm is trying, adversary is trying to minimize the learning. So, in the case of binary search example, the range, what is left is the learning. Right? Both of you know it, I know it. So, you know what is the range left to find the answer, I know the same range, we are playing the same game. So, now you ask a question, I will even tell you my strategy, no big deal, right? Right? I am going to say, oh, I am going to give you the bigger range. So, of course, you will ask binary search and you will force it, right? So, everything is open here. Okay. So, similarly, I want to somehow capture the algorithm's learning in some sort of in a discrete way, then everything will fall in place. Okay. So, again remember, what is the adversary's job is to answer comparison coming from the algorithm. It has to have a strategy. You pick some two numbers and ask what is larger, what is bigger, I have to be able to answer that. So, let us model this thing as just like we had this connected component was sort of a picture of what is learnt in the max finding. The range is the picture of what is learnt in the binary search example. Here, suppose I partition my input into 4 parts. Okay. So, these are N, L, W and LW. This is the partitioning of all the N elements, and this is the meaning. So, I am going to, a comparison is like a game. I am going to use the game terminology, it's convenient, so never played. N means never played. L means lost all the games it has played. Similarly, 1 all played, and LW means the last sum and 1 sum. And this is a partition of the elements into these 4 buckets. And let us use small letters to write down the cardinality of this sets. Okay. So, when I started off, what are these values, these cardinalities? Initially N0, 0, 0. When you end, When the algorithm is finished, what should it be?
I mean 0, 1, 1 and minus 2.
0, because you can't have anybody who has not played anything. There must be somebody who has lost everything it has played. Then that's a candidate for the min. Similarly, there must be one. If you reach that state, you are sure you found the min and max, because these guys have lost some and won some, so they cannot be min or max. Right? They are out. So, and this guy has won everything it has played with, so it must be the max. This guy has lost everything, so you want to reach that stage. So think of it, the whole game is a big state diagram. You have a state diagram where it's the state starts with this, and you want eventually you want to reach here, and every comparison moves you from one such stage to another stage. Okay. Now the algorithm wants to go from here to here quickly, and the adversary job is to make you move slowly, right? You want to find the path to be large. Okay. Once you set it up, what should be adversary strategy is very clear. Okay. I'll just tell you, or at least. So a comparison comes, the algorithm, the adversary has to answer. Right. Now comparison between two elements are coming. So I look at which set it is belongs to, right? So I have this XY comparison. There are several possibilities. X is in L, Y is in L. What should the adversary answer? Arbitrarily, right? Both have lost all the games so far. I will answer arbitrarily. So one of them will move to LW from L. So one element will move from here, right? So if I answer arbitrarily, then if I started with, let's say, X or A, B, C, D was the state, after this comparison, A remains A, B will become B minus 1, C remains same, D will become D plus 1. Okay, so I will answer arbitrarily. Similarly, if X is in W, Y is in W, okay, some move. So if you think about it, something decreases by 1, something increases by 1. So this is the crucial thing. If X is in L and Y is in W, what should I answer? Again, I have two possibilities. Let's check it out and then see what makes you move faster, right? Because so if X is in L and Y is in W, suppose I say that this guy won and this guy lost, then what happens? The LW list increases by 2. LW list increases by 2. But if I say, no, this guy lost and this guy won, what happens? Nothing changes. So my strategy would be to say that Y wins, X loses. Then you remain in the same state. Right? Now you can write down all the comparisons and then see what is the effect of moving from one state to another. And based on how fast you move, adversary will give the outcome. Okay? So, you can write down, somebody is in LW and maybe Y is in W. How should it answer? How should it answer? X loses, Y wins, because because if I move Y to lose, then this guy moves to LW. I don't want to increase LW because ultimately LW has to increase to N minus 2. I want to make that process slow as an adversary. Right? It's an open game. You know what this is, right? So now this is in N and Y is in N. Answer arbitrarily. If X is in N and Y is in L, what should it be? Y should lose. X wins obviously. So X moves from N to W, but Y remains. That number remains, because if X wins, then your LW increases. X has to move from N to somewhere. It doesn't matter. That's not a big thing. LW increase, and LW increase is I want to eventually they should go from 0 to n minus 2. I want that to a slow process. Now let's capture so the strategy is clear. Once you write down all possibilities, the algorithm strategy is to make this move very slow, right? Now, where do I get this number, right? Let's see, how do I go from here to here, right? How should n becomes 0? What is the fastest way to make n 0?
Every time ask from
To compare two elements from here.
Compare two elements from n, right? Because then both of them move somewhere. One goes to L, one goes to W. So how many comparisons you need? N by 2 for this to become 0. In all these comparisons, nothing moves to LW, right? The way I will answer, whenever you are making these NN comparisons, LW does not increase. Now, so you can move from here to here, you can say, so in this big state diagram, all I'm going to say is to move from here to here in my strategy, you need at least 3n by 2 minus 2 comparisons. And why 3n by 2 minus 2? Because to go from here to reach your 0 requires some n by 2 comparisons, and then for this guy to move to n minus 2 requires an n minus 2 comparisons, because I will increase my LW only by 1 all the time, the way I am answering it. So it will be n by 2 plus n minus 2, and that's what this 3n by 2 is. Okay, so this is, it gets a little non-trivial because somehow you need to capture what the algorithm is trying to learn in some sort of a discrete way, and then you answer in a way that the algorithm is not learning much. Now, see, immediately this gives you the best algorithm. So what should be the best algorithm's choice? Make the n go to 0. That's what it did. You did the pairwise comparisons to find the max, remember? And then I picked two guys in L and made comparisons. That's the losers playing games, right? And when I pick two ions in L, one of them will move to LW. LW 1 by 1, it's increasing, and eventually it will increase to n by 2. No, so sorry, this is not, no. So this is the first round comparisons. Then I play the W's, the winners. So whenever I play the W, the LW also increases because one of them will lose. LW increases to some half, and then I play the L's to make the other LW increases by another half. So that's what the comparison algorithm is, right? So just like binary search. This adversary argument told you that the best choice is to ask the middle. Similarly here, an adversary argument will direct you to a good algorithm as well. So here, typically adversary arguments give you stronger lower bound, and it can make the algorithm tight. Okay, I think I will stop and we will see more in assignment. So it's a good just flavor of, there are not too many lower bounds known, and essentially we saw three things. One is decision tree information theory, other is adversary, and the other is reductions. Reductions are also very useful. Once you know a lower bound for something, use it to prove a lower bound for something else. Okay, fine. So next week onwards we will move on to graphs.